Thank you, Antonino. And thank you to everyone who's, if I stand here, can you hear me all right? It's a good room. I don't like to. No, no. All right, move the microphone over. All right.
Like this one, probably.
No. Thank you for having me. It's a huge honor to give the Rita Levi-Montalcini lecture. She is indeed a role model, especially since she lived to be 103 and still had a, I've decided she's my next role model for that, and of course, the wonderful science she did. As Antonino told you, I'm trained as an engineer, and before I start, I want to bring greetings. Oh, can you bring the whole, this is showing that's it? Oh, okay. All right. This shows my research group in Southern California. I'm at the California Institute of Technology. Should any of you young people want to wander over to Southern California, it always looks like that. And of course, the students are happy, but this was on a break that we took at the beach. They do all the interesting work. I get to go around the world and talk about it, but of course, it's their creativity that makes it possible. So as you heard, I'm an engineer. I was trained at the beginning of the DNA revolution. This room is really good acoustics, so you can hear everything that goes on here. I was trained as an engineer at the beginning of the DNA revolution. So instead of building oil and gas facilities, which is what most chemical engineers did at the time that I was trained, I decided I would become an engineer of the most complex and beautiful things that I could imagine on the planet. And of course, that's the living world. And as a chemical engineer, I was interested in how they did their chemistry. This was when it was very difficult to engineer proteins. So I said, I want to build new enzymes, the catalysts of life, to do chemistry that would be useful for human beings. But no one had a clue at the time how you would actually do that. So this is a wonderful place to be, to have a vision at a time when powerful new tools come in, and you have to figure out how best to use those tools. So here I was, a young engineer, wanting to build new enzymes. I'll tell you more about enzymes. I'm sure you're all biochemists and biologists, and you've heard about enzymes. But for me, this was a revelation that nature could carry out chemistry with very little waste, recycling everything, and using renewable resources that she could just pull from the environment. That's a wonderful model for how human chemistry could be. Now, it was hard to do protein engineering then. This was around 1982, 83. The first protein engineering experiments, the first site-directed mutagenesis experiments were just being performed at the time. And basically, it would take weeks to do anything. Now, if we fast forward 40 years, of course, we are spoiled now. You can read any DNA you want. Sequencing is very inexpensive. You can write any DNA you want. So synthesis of DNA in any given sequence, you can just email that off to your favorite supplier and get the physical DNA back in the mail. We couldn't even imagine that 40 years ago. And you can edit any DNA you want. So my friend Jennifer Doudna and Emmanuel Charpentier won the Nobel Prize in 2020 for being able to go into a living cell and modify DNA as they would want, more or less. So read, you can write, you can edit, but what we couldn't do in 1985, and what we still are having struggles with today, is composing. So this talk is all about how you compose the code of life to be better than what nature does, at least by my definition, to perform tasks for human beings that perhaps nature never thought would be useful, and therefore you can't go out into nature and find it. So how do you compose? And believe me, our ability to compose, to me, it's like a Beethoven symphony, even a single enzyme. And I play the kazoo very badly. So we are a long ways away from being able to sit down and write out that code. Although AI might come along and potentiate that. So to me, as a young engineer, instead of doing what was done in those early days, which, by the way, protein engineering was owned by structural biologists. And structural biologists think that the structure is the requirement. So you had to get a crystal structure, use your big brain to read that structure and go in and manipulate the enzyme in a way that you thought would be beneficial. And that never worked. There were so many, I say, tears and beer stories at Gordon research conferences from the students who did all these experiments that never worked, and of course only the successes were published, so you thought that we knew how to engineer proteins, but that was all wrong. And I learned that very quickly, that sitting down and designing a new enzyme would never solve the problem. So I turned, in fact, to the most powerful design process that was ever invented. And it wasn't rational protein design, it wasn't AI, it was called evolution. Evolution gave rise to all the magnificent enzymes that you can find in the biological world. And it just came about by a simple algorithm of mutation and natural selection. Just turn the crank of mutation and natural selection, and all this functional variety was created. So why not use that process as a forward engineering process, as a way to explore evolution into the future? That was my brilliant idea, but of course we had no idea how to do that on a time scale that would work for a young professor who has to get tenure and big publications in a short period of time. So that's what I'll tell you about. Evolution is a cool idea. It's not a new idea. Of course, humans have been using evolution to create new biological entities for thousands of years. Evolution by artificial selection, we've fed ourselves, we've made companions like these dogs. We've made things that aren't remotely natural. That poodle would be eaten in my neighborhood. It's not even fit. It would be eaten by coyotes in my neighborhood and wouldn't survive and reproduce. But we have created these biological things through artificial selection. Now, the mechanisms for diversification, so we all know evolution is based on the diversification of DNA. So sex is great, recombination is great, mutation is great, all the mechanisms that nature uses. But if you are the farmer in the farmyard, you've got limited control over that, right? You get to choose who mates with whom. Geese go with geese, and monkeys go with monkeys, worms go with worms, but you're not going to cross monkeys and worms, for example, and get anything useful. And our control in the barnyard, at least, is over mutation is very limited, and maybe you can go out and smoke some cigarettes later, dial in a few random mutations, take a few transatlantic flights, but really we don't have any mechanism to control that underlying DNA process. But of course, now with all the tools of molecular biology, that's completely changed. In the test tube, and this was the vision that we had 40 years ago, you can make anything you want. Right? You can use all these tools now to change the underlying force of evolution. So you can recombine monkeys and worms. You can have 3 parents. You can have 33 parents. You can dial in any level of mutation you want. And I introduced Wolford. Wolford is my laboratory mascot. He is here just to get you to think about, oh, wow, if I have control over all the DNA that underlies evolution, what would be my process? What would be my algorithm for making something useful? Before I tell you a little bit about how we thought about developing that process, I want you to think about where we could go with this. So as Antonino mentioned, there's a universe of possible proteins. How many biologists in the audience? Just about everybody, right? So I'll insult you first. Biologists tend to study this tiny little green fraction, and biochemists tend to study the little fraction of that protein universe that has proven useful to nature, right? That is proven useful to organisms, and therefore come through the process of evolution. And I'll tell you that all of the proteins that nature has ever tested and thrown away or kept are just the tiniest fraction of the number of possible proteins out there. As an engineer, I'm really excited about that universe of possible proteins, because there lies, well, let's see, solution to the energy crisis, cures to cancer. Why, there might even be the solution to death and taxes out there. I think there is, but you have to find it, right? So the challenge is, how do you explore the adjacent possible? How do you start with something, for example, that you can scrape off the bottom of your shoe and go out and explore this space of fantastic proteins? That's not obvious. It wasn't obvious, at least to people working on this at the time. A number of people thought about evolution as a process for exploration. But I think it's important to think about the numbers here. They're really big. And so, for example, Antonino mentioned an inspiration that I had, which, if you haven't read the short story by Jorge Luis Borges, The Library of Babel, is probably the best description of the protein universe, or the Library of Mendel, the Library of Maynard Smith, all these possibilities that biology has to explore. This is a wonderful description, and it's a short story, so it's infinitely worth reading. And the numbers for proteins are beyond comprehension, right? We have a small protein, 300 amino acids long, 20 letters in the alphabet, has 20 to the 300th power possible proteins, which is bigger than the number of particles in the universe by 85 orders of magnitude. So it's incomprehensibly large. It's bigger than the United States national debt, which is a number that you can comprehend, perhaps. I mean, this is a really big place. And if you just make changes to 1% of the sequence, 3 amino acids, you already have, billions of ways to do that. So we can't begin to explore this space in any comprehensive way. At least we couldn't in 1985. So how do you explore this space to find something useful, not just functional, but actually that solves a specific human problem when you've got all of these possibilities? And believe me, the experimental possibilities, even today, when people throw out big, I can search billions of things. Well, billions is not very much compared to this space. So experimentally, it would be hard. Now, there was another important short story that I read. It was written not long before I was a graduate student. John Maynard Smith wrote a 1.5-page paper in Nature about this problem that really changed the way that I looked at it. And I do recommend all young people read this paper. It's amazing because back then, 1970, he didn't have sequences deposited in databases to look at from which he could build family trees of proteins and see how evolution progressed. We have those sequences now, and so we can actually see molecular evolution. But you know what he did? He sat down and he thought about it. And he thought deeply about it, and he says, well, to search this space, and if evolution is true, and I believe it is true, that tells me something about how protein sequences are ordered in the space of all possible proteins. He said, imagine proteins of a certain sequence are surrounded by all their single mutant neighbors, and those are surrounded by all their single mutant neighbors. And so obviously this is a thousands of dimensions space, but everything is surrounded. And he said for evolution to work, one has to be able to walk from one sequence to another through single mutation walks. Because making multiple mutations, the probability of function is too low. And we have to more or less walk one step at a time. Now that's something even an engineer can understand. And it's something that I could use. In other words, there must be functional proteins near where you already have a functional protein. And if that's the case, that there's at least one functional protein nearby, one can walk through this space to find new proteins. Now, of course, I didn't want to just find new proteins. That's what evolution does. Usually it's just a neutral walk through sequence space. I wanted an adaptive walk. I wanted a rapid uphill walk in function by taking as few steps as possible. This would work only if the fitness landscape looks more like the one on the right than the left. Because imagine if the landscape is very rugged, you take a walk, you fall into a crevasse of non-function and evolution stops. And Maynard Smith said that's not the way it's going to look, because we need to be able to take single mutant walks. And for an engineer, that tells me that at least in some of its dimensions, the fitness landscape has to be somewhat smooth. And if it's a smooth landscape, any fool can optimize on that, because you just close your eyes and take the first step uphill and keep going. So that can be translated into an experimental process that's very simple. You take literally a sequence from the bottom of your shoe, the product of 4 billion years of evolution. A lot of work embedded in that product. And you can change it along the direction that you're interested in by making a few mutations, not many. And this was really the difference between what I did and what everyone else who tried this in the early days did. I said, make just a few mutations, because you want to average a single mutation, because you don't want to fall into non-function. And of course, we use recombinant DNA technology, so you put that DNA into bacteria, they read it, they make it, you use the tools that were easily available at the time, and then you screen that library, only a few thousand, right, because there's only a few thousand ways to make a single mutation. And it turns out, if you screen carefully, this was very important, you have to screen with a low coefficient of variation. I studied statistics, I understood this, and you have to screen tightly for exactly what you're interested in, and you have to make that screen sensitive enough to the effects of a single mutation. Right? You're not going to get a 100-fold increase in activity with a single mutation. You might get a 2-fold increase. So we have to be able to find that in a sea of things that are not better. But if you do that, we found almost always there were improvements in functions for which nature had not selected. And that's important. Nature's already selected a function. It's rare that you find improvements. Not always, but it's usually rare. But if you're asking it to do something new, where there's a lot of room for improvement, we could easily find those modifications. Most mutations are deleterious, so those in the old days went into the trash can, and I bet you can guess where they go today. But I'll leave that open. But then you take the ones that are better, and almost always we found multiple, we would recombine those and feed it back into the process. And that gave you a very powerful process that looks like this. You start with something that nature made, doing its natural job. It's generally pretty good at it. You're near the top of a fitness peak. You ask it to do something new. So you move over to the red fitness peak. That's a new request. And it's generally less enthusiastic. Enzymes are kind of like people. You ask them to do something new, they complain about it, fitness drops, but you train them and you push that process. You turn the crank of mutation and artificial selection, and you can push that up a new fitness peak. And that process turned out to be very robust, and we could do all sorts of useful things. My motivation, and I won't go into this too much, came from the chemistry side. I wanted to replace all chemists with bacteria. Any chemist here? Good. But you're here, so you must love evolution. But I'd love to yank the chains of the organic chemists. Someday, I think that we will be able to replace almost all of organic chemistry with clean biological systems. where the chemistry is encoded in DNA, and I will show you more about that. But again, using the renewable resources and the real specificity and selectivity of biological processes to minimize wastes. And of course, when you develop a process that's easy to implement, everybody uses it. And so I'll just say over the last 30 years, people, not I, but people in general in all sorts of laboratories across the world started using directed enzyme evolution to make everything from the reagents in your DNA sequencing machines to processes for making all sorts of pharmaceuticals, the enzymes in your laundry detergent. What self-respecting biological enzyme wants to work in your laundry machine? They don't. So they are turned off by surfactants and bleach and all of that. But if you evolve them, they become very good. And that has lowered the energy costs of, I know this sounds like a silly example, but it's actually really important. It's lowered a lot of energy demand of cleaning. So for that, I got the biggest accolade of my life when I was asked to go down the street to Warner Brothers Studios in Burbank and play myself on the Big Bang Theory. Who here has watched the Big Bang Theory? Yeah, a good nerd audience. Okay, that's great. For those of you who haven't had the pleasure, the Big Bang Theory is a TV show about graduate students in physics at the California Institute of Technology. They're endearing as graduate students, but then they go on after 12 seasons to become annoying professors who are lobbying for Nobel Prizes. So it's really good. But the show is over. But please do go and watch the Nobel accumulation. I was the first woman ever to play herself on this TV show. And if you watch it, I get like 2 cents every time you watch it because the residuals, it's a racket, I tell you. But I had a great time I wasted a perfectly good morning going down, appearing on this. You may recognize, if you're a physicist, Kip Thorne. he's over here, Kip Thorne. Anyway. That was a lot of fun. I also got invited to a very cool party. And I have to say, it's cold and dark in Stockholm in December, but they lit up this little house for us, and we had an amazing party. This is 3 in the afternoon, so it's definitely cold and dark. It's such a good party. I have to say, if you ever get invited, you should go. That's all we need to know. So what did we learn from 30 years of people directing evolution? And we learned this early on. First of all, proteins adapt very quickly. And anybody who studies antibiotic resistance or viral evolution or pesticide resistance knows this. Well, a lot of people didn't appreciate it at the time, that if you accumulate mutations in a simple uphill walk, that very simple strategy works well. You can get new functions by changing just a few amino acids. This we didn't know because biochemistry, of course, contains all the neutral mutations. So 2 enzymes with different functions might differ by 100 amino acid substitutions, but very often you can get the same sorts of effects with just a few. That saved my life, right? Because every generation took weeks or months in the early days. And if it had taken 50 substitutions to change function, I wouldn't be here to talk to you. Now, here's the scary fact for would-be Beethovens. If you think you can sit down and design a protein from first principles, see, physics-based design, and I used to get into trouble with David Baker by saying this all the time, it's never going to work. Most of the mutations that we find, this is an observation, most of the beneficial mutations that we find can lie 20, 30 angstroms away from the active site of the enzyme. Nobody can explain those mutations, much less predict them. And that's still the case today. We cannot explain these. And why is that? It shouldn't be surprising because a 2-fold increase in activity is a very small energetic difference. Often within the resolution of a crystal structure or there's dynamics at play, we still don't understand enzymes at this level to be able to predict beneficial mutations. And so there's still role for experimental evolution and certainly learning from data. All right, so I have just spent all this time telling you about this ultra simple, ultra stupid optimization strategy that really works. We can optimize enzyme function starting from what you find in nature in real time. But that's not what I want to tell you about. I want to tell you about innovation, not optimization, but innovation. How can we create a whole new function? I started getting interested, this is a little science sociology. People love to compare themselves to others. I started getting annoyed by my friend David Baker, who he made all these terrible enzymes starting maybe 15 years ago. And he started making, through rational design, enzymes that would carry out chemistry you cannot find in the database, that would do chemistry invented by human beings. Terrible chemistry, but new chemistry nonetheless. And it's so annoying because it would take 7 rounds of directed evolution even to get them publishable. But it was annoying because he was doing something I couldn't do. Because think about it, or at least this way I thought about it 20 years ago. To get a new function, you have to correctly, and this is the way he thought about it, you would have to correctly position multiple functional groups to lower the transition state for your chemical reaction. And as you know, as I just explained, positioning multiple amino acid side chains simultaneously through a blind process is highly unlikely to give you anything that you can actually select for. So I just stayed away from that problem until 2010 or so, and then I said, this is just too annoying, and I realized I had been thinking about it all wrong, right? So it's not this positioning of multiple functional groups simultaneously, although that's how design is doing it, because nature is making new enzymes all the time. Evolution has not stopped, and nature solves new chemical problems by evolution. She doesn't sit down and design a new protein. Let me give you an example. Here's a potent herbicide that we've been dumping on the planet for 60, 70 years. And at first, it was non-biodegradable. But then, after 50 years or so, this activity for dechlorinating atrazine appeared. And once it appeared, it went all over the planet because the enterprising bacterium that figured out how to pop that chlorine off had a tasty, rich nitrogen source that gave it a selective advantage over its neighbors. And that enzyme went all over the world. Now, you're not going to create a whole new active site in 50 years. That's going to happen by a process that I just described to you. And so the solution was that nature's innovation came from what was already there. In other words, there was already out there in this huge diversity of genes on the planet, there was already an enzyme that had a little bit of what we call promiscuous activity for atrazine, for dechlorinating. It wasn't its natural function, but it was capable of dechlorinating atrazine. And therefore, once that gave a selective advantage, just natural selection pushed that activity up. And this was such a nice example. I said, here's the solution. Enzymes are promiscuous. They're kind of like, sorry, are there any graduate students here? You're next. Okay, nobody's going to raise their hand, but they're kind of like graduate students. Not that graduate students are promiscuous, it's that they're multi-capable. And enzymes are the same. They may be selected for one job, but they can go out and select it at low pay to work long hours, but they could also do dishes or play the piano or become an Olympic Taekwondo champion. They have many capabilities that should the environment change, they can go and do something else. Enzymes are just like that. And so I'm the one that makes the environment change. And so my ability to innovate, to drive this process, comes from recognizing what the enzyme could be capable of doing. So let me give you an example. And this is my favorite example because there is no enzyme out there in any database except for mine now that you can go and say, give me an enzyme that breaks carbon-silicon bonds. Here's the second most abundant element on the planet, and there are no carbon-silicon bonds, yet there are 50 products in this room, from your hair gels to your caulks and sealants and paints and earbuds, that have organosilicon components. It's a huge industry. It's a very dirty industry, uses platinum to make those, but never considered biology because these worlds don't intersect at all. So we said, okay, can we make an enzyme that can forge carbon-silicon bonds? And to do that, we had to kind of propose what enzyme would have that capability. And I was working on these cytochrome P450s at the time that can take molecular oxygen, create a highly reactive iron oxo species. And we said, okay, could we convince this enzyme to instead make a reactive carbene? And if you go to the literature invented by chemists, so you go to all the old papers invented by chemists, you can find metal complexes, never iron. They never used iron to do that, but you can find transition metal complexes that would interact with a carbene precursor and create a reactive species like this carbene. And also transfer it to a second compound. So we said, okay, does this look enough like oxygen to a P450 to convince it to have this new capability, take a reactive carbene and transfer it to a second substrate? Absolutely no precedent for that other than the fact that carbene precursors can inactivate cytochrome P450s. There's no evidence that they transfer. So we just said, can it do that, and does it evolve? So I'll tell you about a funny little protein we decided to study. This is a cytochrome C from a hot, salty pool in Iceland. I just pulled it from the database. I like this one because it has no catalytic activity. It's an electron transfer protein, but has a nice, stable structure. It's so stable. It's so stable you can give it to a chemist, and they won't even know it's a protein. You can lyophilize it, put it in a bottle, don't tell them it's a protein, and they can use it for this chemistry. And you can even boil this thing. And we asked it, and other proteins, we said, if I give you dimethylphenylsilane and a carbene precursor, like that diazo compound, these are reactive things you don't find in nature, so nature never had a chance to express this capability. Sure enough, the cytochrome C catalyzes the formation of a new carbon-silicon bond. And it does it with very good enantioselectivity, which tells you it's happening in some sort of active site that imposes this selectivity, because if you were just in solution, you'd get 50% of the 2 enantiomers. So it's very selective for this. And we were thrilled because 40 turnovers was as good as any human chemist had ever reported using iridium and gold and things like that. Here, earth-abundant iron in a protein was as good as what people spent years trying to develop. I was thrilled. All right, so I'm sitting there talking about this when an expert on cytochrome C is sitting in the front row where you're sitting now. He jumps up and says, oh, but Francis, how can that be? Don't you know that cytochrome C has no active site? And in fact, if you look at the three-dimensional structure, you would be talked out of trying this experiment because cytochrome C has a methionine above and a histidine below, and all the other sites for interaction with a substrate are occupied by the nitrogens in the heme. So if you roll your little computer ball over the active site, you get a big fat 0 for volume of the active site. But I'll tell you, nature really does not care about your calculations because protein catalyzes the reaction. And not only, I mean, obviously our description of this high-resolution crystal structure is not sufficient to tell you what's actually happening in a moving protein because it catalyzes the reaction. And not only does it catalyze the reaction, it evolves. So you can direct mutations. Jenny Kahn in my group directed mutations to the active site and found just over 3 generations, she could make something that was 50 times better than the best catalyst reported then by a human being. And that was enough to get published in a snooty journal, so we stopped the evolution experiment. But it showed not only does it do it, but it evolves. I'll just point out for the biochemists in the group, one of the most important mutations was that ligating methionine, it got turned into an aspartic acid. And that was a critical, there were 3 critical mutations here. And that M100D from the first generation was important because instead of ligating to the metal, it now interacted with water. So it pulled the whole loop over the protein. This whole loop now created an active site where you could sequester a substrate. And that's how we got perfect enantioselectivity from this. I'll just point out these interactions with water, we still can't design those. And that's very, very difficult for AI to get. So these kinds of solutions that we're getting here are still evading any of the tools that we have for making such active sites. So I published this work. Actually, before I published it, I was out talking again, and this time sitting in the front row was a reporter from Science magazine. And he said, oh my goodness, this is so cool. I have to write about it. And I said, well, you know, my paper's under review at Science right now, and I have to zip my lip. You're not allowed to do science by press release. So he made up a story. He said, researchers take step towards silicon-based life. I said nothing about silicon-based life. Absolutely nothing. And if you read the science paper, it's the most boring chemistry paper you can imagine. Very, very straightforward. You know, we made an enzyme that catalyzes this simple reaction. 130 pages of supplementary information because chemists want every single stupid compound you made fully characterized, and we made 21 completely new to nature silicones that nobody cares about. And so no one read the paper, right? I don't think anybody read the paper, but they all read this. And so the news, and then you can see, you know, they brought in Star Trek. Anybody seen the Horta episode when they're looking for the life in rocks? That wasn't us. We were looking for, you know, putting rocks in life, but not really. None of this had anything to do with the paper, but people loved it, absolutely loved it. When you bring Hollywood in, it really helps. So it went around the world, the news went around the world. Maybe Popular Science read the paper because they actually knew something about chemistry, and they said, silicon-based life, I don't think so, and there are very good reasons why carbon-silicon bonds are not found in biology, but I never claimed that. And then Astrobiology magazine came in and said, oh, we like this idea, and all 17 readers of Astrobiology magazine clicked on that, making it the most popular article of the year. And then we come to the intelligent design community, and they said, ooh, this must be intelligent design. I said, yes, I am the intelligent designer because I'm using evolution. And the best part was when you get to the old Twitter. I don't know if you're on Twitter. If you want a funny review of your work, go to Twitter all the time. We were rolling on the floor laughing, and these are just a couple of the comments. We had hundreds of comments from people who were engaged in this idea that the chemistry of biology could expand very easily. I mean, if I can do it, anybody can do it, can expand very easily to chemistry that people thought was not relevant. And that opened a lot of opportunities because Dow Chemical, for example, read that paper and they said, ooh, you know, maybe you can make carbon-silicon bonds with iron. That's a whole new research area for them. But even more important, if you can make them, and I believe if you make them, you should be able to break them. And they want, you know, silicones are not biodegradable. We're making 1 billion pounds of these things every year, and they're accumulating in the environment. Some of them, some of the breakdown products and some of the smaller versions are banned in Europe and are likely to be banned all over the world. And of course, there's no enzyme known to break these bonds. So they funded research in the group, which culminated in a publication last year on enzymes that, the first enzymes that break carbon-silicon bonds. So we're taking a small step towards biodegradation of these things. It's really hard. The analytical chemistry is a nightmare for these, but I hope that one day we'll see new biological systems that can break down these things. But I'll just point out, in the course of 2 years, we were able to add 2 whole new elements to the periodic chart of carbon X bonds of biology, right? There's whole swaths of black on this chart where carbon X bonds have never been observed. And it was very easy to do silicon, and now we also did boron in 2017. I'll leave the rest of the periodic table to you to fill in, but it's kind of fun. Now, once you have a new mechanism, so this carbene transfer is a really big area of chemistry. There are so many things you can do with reactive carbenes, and we've done hundreds of new chemical reactions now, building out. So once you've got something that'll do cyclopropanation, you can do all sorts of other CH insertions, BH insertions. I mean, we can make crazy things like cyclopropenes and bicyclobutanes. No human chemist can make those with selectivity. And we can make single stereoisomers of these highly energetic compounds and a whole bunch of other useful things. And it doesn't stop there. If you can do carbenes, we also showed early on that you could transfer nitrogen. So that's, instead of transferring oxygen, we first transferred carbon, making new carbon-carbon bonds, and now we can make new carbon-nitrogen bonds, again copying chemical ideas invented by human beings. So we make nitrine transferases, and I'll just give you one example because it's, I think, shows very compelling what you can do if you can train these enzymes to do completely new chemistry. Here, Gigi Li was approached by the Bill and Melinda Gates Foundation to make these oxazolidinone antibiotics that are the first line of defense for tuberculosis. And they're too expensive for widespread use in Africa. So they said if you could make enzymes that make this core, this oxo core of these succinylide and other compounds, we'd like to know if there's an enzyme that could do that. And so Gigi and others in the group figured out that if you could aziridinate that double bond and then get the enzyme to do ring formation with the right stereospecificity, you could bypass about 7 chemical steps in the synthesis process. You could use one enzyme to do what 7 chemical steps in the expensive process would do. And this is why enzymes are so powerful in synthesis, because you don't need to do protection, deprotection, and all that. And so you could bypass that. And sure enough, we found a couple that could do a little tiny bit with really poor selectivity, but then we were able to evolve that, and now we have enzymes that can make these cores in a single step. And I'm hoping that this will go on and improve production. I'll just point out a comment that Derek Lowe made. Derek Lowe is a medicinal chemist who's very critical of the literature, but he, it's sort of a buried criticism here. He read our paper on when we published enzymes that could just plug an amino function onto an unactivated CH bond. No human chemist knows how to do that. I just showed you with the OXO antibiotics enzyme that does what human chemistry can do in 7 steps. Here's a step that no human chemist knows how to do, and that's to add an amino function unprotected onto an unactivated CH bond. And when we published that, Derek says, here's a reaction that looks like alchemy to those of us in the synthetic organic community. They look like magic. They do chemistry that can't be done with the reagents we have now. But it's not magic, right? There's nothing magic about it, because we're just doing what humans have been doing for a long time, manipulating transition metal complexes, only we're doing it in a self-assembling, fully DNA-encoded chiral metal complex that's called an enzyme active site. So there's nothing magic about it. It's just we have a platform for manipulating chemistry that nature developed and has used for millennia, for many millennia, to do interesting new chemistry. So let me finish with where the field is going, because I know we're going to hear a lot more about that today. And I love the program for the workshop. I look forward to hearing some really excellent talks. Starting in 2012, we're generating a lot of data. And it's pretty clear if you're generating data, you can throw it into the trash can, right? Which is what we did for many years because we didn't have labeled data. We didn't have sequences to go with all those bad variants. Today, we sequence everything because sequencing is really inexpensive. We sequence everything, and therefore we can label the bad ones along with the good ones. And if you generate data in every generation, then we can get away from this limited process, right, where you're taking a random uphill walk. That can be slow if you go in the wrong direction. You can get caught on local minima because it isn't fully Fujiyama-like. Real proteins have multiple peaks. And we want to get beyond being stuck with the old-fashioned directed evolution. So, it's painful. There's nothing enjoyable about doing directed evolution for the third time. First time is fun, second time is less fun, third time you've had it because it's an algorithmic process. So we would like to speed up and potentiate this process. So in the new days, of course, we take all the data and use those to build machine learning models, feed that back into the process and in an active learning cycle. So we do active learning, guided directed evolution in order to navigate a more rugged, realistic sequence landscape. And of course, with neural networks, we can combine data from all sorts of, we can build multimodal models that combine data that we have. We have knowledge. We have all sorts of evolutionary information. We can use protein language models. We can incorporate structure and dynamics and quantum mechanical calculations. And so now we can build models that use those in order to navigate. So my vision, and this is where we're going, is that we will be able to, sorry, I want to go back here. We want to use generative AI. This is the next frontier, right? I'm doing the adjacent possible. I'm taking what nature has given me and moving out. But why limit yourself to that? There's that whole space way out farther where generative AI can take us. It's still very limited for enzymes, but we're getting better all the time. And so if you can envision an enzyme a la David Baker and create a whole new scaffold for that chemistry, even if it's terrible, you can incorporate that into the process and optimize through directed evolution. So my vision is that we will be able to do the pre-training and make big models on lots of public data, and then steer those models with data. So actually steer the pre-trained models, steer the models, and then do also active learning on the optimization. The net result will still incorporate experiments, because I think we're far away from just jumping to a perfect enzyme, especially for non-natural chemistry, which by definition is not in the pre-trained data. It's well outside the distribution of the pre-trained data. But with a little, what we're finding, and we collaborate with all sorts of groups around the world, what we're finding is that with a little experimental data, we can quickly converge on enzyme space for new chemistry and then optimize that. So if you're interested, we've written lots of papers about this, and I'm working towards this vision. So back in 2022, I wrote on Twitter that we will be able to press a button and create any enzyme we want. This is my vision, right? To genetically encode any kind of chemistry. Just press a button. You can automate everything in the experiment. It's an algorithmic process. It's boring, it's repetitive. Robots could do it. And don't tell it to my graduate students. They would be hugely offended. But a graduate student made this with the early DALL-E. You remember DALL-E? That made this wonderful picture of the graduate student pushing the button. Now, of course, this was on April Fool's Day, 2022, but it wasn't a joke, right? Because now here we are in 2026, and this is becoming, we can now see this as a reality. It's not real today, but perhaps tomorrow it will become a lot more real. I had the pleasure, and I'll end here, I had the pleasure of spending 4 years in the White House as the advisor. I was co-chaired the President's Council of Advisors on Science and Technology. That's one of the costs of winning a Nobel Prize. They think you know more than you know, and therefore ask you to give advice on things you don't know anything about. There I am yammering at I actually do know something about AI, but not huge amount. I'm yammering at the President of the United States about AI, how it's going to, use all the data in the Library of Congress and the internet and his bank account, and he says, well, they won't find anything there. He was sharp. He was sharp, and it was fun to work with him. But I'll just point out, we had, under this administration, 30 of the top scientists and technologists in the country volunteering, this was a volunteer position, volunteering their time to advise him on climate change and public health and a number of issues. That's not the case today. All the members of this council today are tech billionaires, so you can, and cryptocurrency. So it's a different situation. I hope we'll get back to where science can really advise. But when I took the job, it was in January 2021. And I'll remind you where we were in January 2021. We didn't have vaccines for COVID. Our parents were dying in nursing homes. My mother died in a nursing home in 2020. We were suffering. We were suffering. To do the job, and I didn't feel that I could say no. But when we were rolled out on television, we got some good nerds here. In binary code on the wall there, spells out these words: hope over fear, unity over division, science over fiction, truth over lies. That's not a political statement. Of course, it was a political statement, but it's really something that science should offer us. Science is a public good that offers us the knowledge and the ability to move forward and to do good things for people. So I hope that you all will see it the same way. Thank you very much for having me. I don't know if we do questions.
There's no other word than applause. I think that, thank you. I'm sure there are